אסף, תגיד, יהיה לך דקה לדבר על ה-Zero Shot Super Resolution שכתבת?
אז אני יכולה לשמוע בלי...
אסף, אתה muted?
Hi, everyone. So, hope all is well. And can everybody hear me? Are we all good? Great. So, hope all is well with everyone. And welcome to our third lecture. And today's topic would be convolutional neural networks, which we will define just in a brief. Two things to let you know first. So, as the meme describes, I suppose all of you are struggling with the homework set that we have. So good luck with that, and be happy that once you implement from scratch all this backpropagation stuff, then you will surely be sort of a deep learning expert. There are many people out there that know how to use PyTorch, TensorFlow, stuff like this, but when are against the wall, don't really know exactly the fine details of how this thing works. So I think it's very exciting that you are able to acquire these skills. One other thing is that we posted on Piazza that there is going to be some theoretical bonus exercise. So we're dropping this thing now. We decided not to give it just yet, perhaps in another homework set. So we will not publish a theory bonus question. And what we're going to discuss today is one of the most important developments in the field of deep learning, and probably the reason that made deep learning so popular, and finally, it's probably the reason why all of you are present here, because if we didn't have CNNs, convolutional neural networks, I think that deep learning wouldn't be as popular as it is, and the really amazing capabilities that it has, especially for the visual domain, would not be there. And we had this timeline in our first meeting, but let me just briefly describe that the credit for the existence of CNNs starts probably 1980 by Fukushima, who first suggested this kind of mechanism, and then Jan LeCun towards the end of the 80s combined this with the backpropagation to a more trainable variant of this. Then at the end of the 90s, together with other important people, you had this network called LeNet5, LeNet named after LeCun, and this was the state of the art for recognition of handwritten digits. And then finally, 2012, Alex Krichevsky, also together with many important people, published AlexNet, which was based on GPU computing and was modern and was actually the state of the art for any image recognition, with many other mechanisms that made it as great as it is. So if we have to map it, these are the four main contributions that when we say CNNs, we need to cite these, okay? So we're going to start by kind of an odd question. And I would like to ask you now, this kind of weird question. What do you see in this picture right here? What is this image? So nobody answers, probably because it's a very hard question. So I'll help. What I see, I would say that I see some guy's desk. But now I insist that you do someone try to answer my question. And my question is, how do you know? How do you know that this is a desk? What makes you think this is a desk? Can anyone help? I know it's not an exciting question, but
maybe
the objects located on it.
What are the objects that are located on it?
A keyboard.
Okay, so we say keyboard, monitor, great. Okay, but how do you know that this is a keyboard?
maybe we recognize the texture, the shape, and we know that the object.
You say texture, shape, and I would say I know it's a keyboard because it has keys, which might lead us to our next question. How do you know that these are keys? And we can go on, and eventually you will have to say something like there is a black dot there, or something like that. There is a line, and we'll discuss this just in a second. But let me point out something that you don't do when recognizing that this is a desk. I think that you don't do. So let's say I have this set of features, okay, and let's call them the red features. And there is 1 pixel here and 1 pixel there, and so I have many pixels, and I can have many other features. So, for example, here is another one. This is the green feature, and each one of them takes this set of pixels and does something to them. And it's sort of a hand waving. It's not something I can prove, but intuitively, I'm sure that you can agree with me that when you process this as human beings to recognize what you're seeing, you're not collecting pixels from areas located at different regions of the image. So there isn't much you can do if I have even 20 of these features like red, green, whatever, and I take this set of unrelated pixels. There isn't much that you can do. What we usually do, at least intuitively, it's not neuroscience, just more of an intuition. So let me reverse the process that we just nearly discussed. Before we said how do we know it's a desk? So it has a keyboard. How do we know it's a keyboard? Let's reverse the process. So when we recognize things, so first we would say something. Okay, I see some vertical line here. I have this mechanism, kind of a simple mechanism that can identify a vertical line. And here's another one. And I can also identify some horizontal lines. And given these and some other stuff like white color or something like this over black, stuff like this, but I can say something more intelligent and say, okay, I think this is a key. And the same way I can identify more keys. Here is another one. Okay, I see here many keys. And then I say, okay, what has many keys? I think this is called a keyboard. And following the same logic, I'm able to recognize that this is a monitor and this is a mouse. And finally, I can say that this is a desk. Okay? So I have this hierarchy of things that I was sort of recognizing until I got to this conclusion that I'm seeing a desk. And let's just see just another aspect. What if I just move my head a little bit and the picture moves a bit? So what do you think that should happen to all these things that I recognize? All these, mid features, let's call them, that I recognized. What would you say should happen now?
They should shift.
They should also shift. So it doesn't matter that the monitor is now shifted a bit. It's still a monitor. It's just a shifted monitor. So this is called equivariance, okay? So it means that finally, for my final recognition, it should be invariant to these shifts. So if we try to summarize now all these things that we expect out of a visual recognition network, so let's try to go through what we just saw, and some things that we didn't. So first of all, one thing is that we would want a visual recognition system to maintain 2D structure logic. So this is in contrary to reshaping it to one large vector. We want to keep this two-dimensional view and have this kind of logic and to be able to do calculations that are related to the geometry of this image and not just as a bunch of a flattened vector of features. And here is what we just saw now. So we want it to be shift invariant. Actually, this is called equivariance. We do want to be aware of the shift, but we also want to be aware that this is also a monitor, just a shifted one. Okay, we're not just saying it's the same thing, that they're not the same, but we do know that this is the same thing, only shifted. Another thing that we saw is that we prefer to consider only local correlations. So we don't want to just collect pixels from all over the image and say, this is a feature I have. Eventually we will collect everything from the picture, but at each step, we're interested on just looking at these local correlations. If I look at a pixel from the monitor and a pixel from the keyboard, there isn't really much I can do about correlation between pixels from the monitor to pixels from the keyboard, okay? Here's another thing. What we just saw was a hierarchically growing field of view. So we started from very small objects. It was these lines, and then a key, and then a keyboard, and then a desk, okay? So the field of view, the thing that we named, it's the size of the region inside the image was hierarchically growing as we took forward steps with our process. This is going to be analogous to the depth of the network that we're going to have. The deeper we go, we have a bigger field of view. Another thing that happens hierarchically is the progressing complexity. The ideas, the semantics of the things that we saw was progressively growing to be more complicated. So we started with a thing that is very low level, a line, a vertical line. And then we said something that is already very semantic. This is a key. A key is a concept. Identifying key is not a trivial thing. It's a very complicated function. And then finally, the function that identifies a keyboard and moreover, the function that identifies a desk, and think about very hard recognition tasks. For example, I want to be able to recognize violence in a video. Think how complicated this is. So to recognize violence in video, then I will first have to be able to recognize humans and to recognize humans' hands and legs, and then to recognize actions, and then to be able to classify what actually violence means. And the complexity hierarchically grows bigger. And one last thing is that we want to have reasonable amount of parameters. We want to be able to train this thing. It can be unreasonably big, have unreasonably amount of parameters. So this is going to be what we'll be looking for, and hopefully CNNs, convolutional neural networks, are going to solve these things for us. But let's first recall what we know about fully connected layers. These are the layers that we've been working with so far. And these are called fully connected, and they are called this way because each neuron is connected to all the neurons in the previous layer. And we already know that this is just matrix multiplication, so we can have this describe this linear way. But let's see how this fits to this set of rules that we wanted to have. So why don't you help me here? So what do you say about one? Does it maintain 2D structure logic?
No.
No, right? Because as most of you know by now, when you took images and applied neural networks to them until today, you had to do this reshape, this flattening, right? You took the MNIST digits and you had this long 784 vector. Okay, is it shift invariant? What do you say?
Also no.
Also no, because there are specific weights that are applied, for example, to this X1 over here. And if I shift it all, just, one neuron down, there are going to be different weights. So there is no shift in variance here. Does it consider only local correlations?
No,
What do you say?
because
Anybody?
No, it connects all to all.
Sorry? Again? Okay,
the
so
neuron on the next layer receives as an input all the neurons from the previous
exactly.
layers.
Exactly. So there are all the I wouldn't say correlation, but it sees all the neurons from the previous layer. And so I already revealed that there is no hierarchically growing field of view, and the reason is that the field of view is everything. Every neuron is actually affected by all the input neurons that exist. What do you say about number 5? Does it have hierarchically progressing complexity?
Yes.
Yes. So Raphael
Sure.
says yes, and you're right. This is actually the only thing that that we do have, and we've actually seen this in our last meeting at the end. Remember, we did this JavaScript thing demonstration, and we saw that the deeper the layers are, we have more complex function of the input. Finally, we do not have reasonable amount of parameters, and let's do this, simple math. So let's say, let's think about images, and let's say that I have, let's take easy numbers. Let's say I have an image that is 1000 by 1000 pixels. So the amount of inputs that we have is 1000 by 1000, actually by 3 if it's an RGB image. So it's 3 million. And if we want to have roughly the same amount of neurons in our next layer, then we need to have 3 million by 3 million weights. Okay, this is roughly 10 to the 13 number of weights, and this is just for one single layer. We sometimes have hundreds of layers. So just for one single layer, we have this really unreasonable amount of weights. So sure, there are some things that can be done, but looking at this naively, this is an unreasonable amount of weights. We cannot process such things. So far we've seen what's wrong with what we had until now for visual recognition. So now let's introduce the convolution layer, and we'll start with the 1D convolution, and I'm going to use this color coding here. So you see we have a black stands for weight with value A, and red for B, and green for C. And the way we define is that the convolutional layer can be seen as a special case of a fully connected layer, only that most of the weights are going to be 0, and that the weights are going to recur. We're going to use the same weights over and over. And this is how it works. So the first output that we have uses a predetermined set of a predetermined amount of weights. In this case, we say that the kernel size or filter size is 3. We have 3 weights, and it simply sums, has this linear combination of 3 inputs that match its position. So as you see, it's only affected by 0, 1, and 2. It's not affected by anyone else, and it uses these weights. As for the next one, we're going to use the same 3 weights, okay? And only we're going to shift this by 1. Okay, and now X1 is affected by X1, X2, and X3. And we can go on, and this is how it's going to look, right? So, and I'm sure most of you are aware of, I hope all of you know what a convolution is, and you see this convolutional logic already appears. But let me ask you this, try to help me. So if this is a special case of a fully connected layer, then it means we can express it as matrix multiplication, because this is still a special case of a fully connected. So let me ask you this. let's try to start this together. So what would you say should be the value of this top left value of the matrix here? What should we have here? Any help? A. So this is correct. We have A because we have this output here, which is a linear combination of these three, and and the weight that multiplies x sub 0 is the black one, which is A, and we can quickly follow the logic. And what's going to be the next one here?
B.
B, and I'm not going to keep on doing this because I'm sure that you understand by now that this is going to be A, B, C, and then the rest of it is 0, right? Because x sub 0 of the output is not connected to x3, x4, x5, or any of them. So can anyone just tell me what's going to be in the next row? So the entire row, how is it going to look?
0, A, B, C, 0, 0, 0.
Right. So 0, A, B, C, 0, 0, and then we can look at the entire matrix. And I'm sure most of you know that this is called a Topless Matrix, and this is a way to express convolution. And don't be confused with a circulant matrix. A circulant matrix is a special case of Topless Matrix, which matches a circular convolution. This is when, like Pac-Man, when you go from the other side, you come back from this side. So we're not looking at this right now. Okay, so this is a Topless matrix. And this is a way to describe a convolutional layer as a special case of a fully connected layer. And you should be aware that while this is theoretically a good way to describe it, it's not. It doesn't mean that this is the way we would want to implement such a layer. And let's look at it from another angle. So to be more in the convolution state of mind, so we can look at what we've just done as having this filter. And this filter has 3 weights. And this filter goes along the input to the layer that we have, and every time it multiplies all its weights with the inputs and then sum it. Another way to say it is that you have an inner product, a standard inner product between the filter and the inputs that it currently sees. So it takes the 3 of these and then it calculates x sub 0 here, and then it goes down and calculates these, and so on and on and on and on. And one question I want to ask you. So let's say I give you the input size, okay, and the filter size. So in this example, you see that the input size is 8. We have 0 to 7, 8, and the filter size is 3. And my question to you is, what's going to be the output size? So you have an input size, let's say n, and the filter size k. What would you say the output size is going to be?
Minus
k plus 1.
Sorry, we were all together. Just one. Can someone tell me? Okay.
N minus k plus 1.
N minus k. So I don't think it has anything to do with n, actually. So assuming we have filter with odd size, which is easier to think about. So the output is going to be oh, sorry, I said it. Of course, it has to do with the input size. I'm sorry. The output is
the input size minus 2.
It's going to be. It's not going to be minus 2. It's going to be the input size minus the kernel size plus 1 here. And one way to see it is that, you know, we can go on as long as when we're at the edge of the input, then we can ask ourselves, where is the center of the kernel? So in this case, where we have 3, we had this. Let me just annotate. So we had, when we're here, for example, so you see that we have this one extra.
We are not seeing. Okay, no.
Okay. We have we have this one extra that we can't see. But if this was 5, if the filter size was 5, then we had 2 of these. But we always have this in both sides. So we'll have it also on the other side. So finally, the size that you're going to lose is the filter size minus 1. But I want to tell you that this is the last calculation in this period that I'm going to do. So we're going to talk about strides and other things that you do with convolution. And eventually there is this formula that takes into consideration the strides and the size of the kernel, and also stuff like, is it even or odd, and some very annoying stuff that are very easy to calculate if you do it by yourself or to look at the formula. And I'm not going to deal with all these calculations. You just have to keep in mind that there is this set of rules which is very easy to check them that determines the output size. This is one thing. And the second thing that we'll see just in a minute, in a few minutes, is that actually you're able to fix this. So if you want to have an output with the same size, you can do that. I'm sure some of you are aware of a thing called padding. So we'll see just in a few minutes. Okay, but just keep in mind that the output is not, defaultly, the output is not going to be the same size as the input, and there's very simple logical stuff that you need to consider. Okay, so this is one question I want to ask. Another question is,
I have a question.
Yeah, sure.
Yes. The weights, I don't know if you're calling them yet weights, but the black, red, green, they are the same?
Weights, yeah.
They are the same for
No,
each neuron?
The same, you mean?
No.
Are you asking if the black is the same as the red?
No, the black is for X5. It's the same as the black for X0?
Yeah, sure. Yeah, this is, if it weren't, then we would lose the point. You see the matrix, this A here and A there, it's the same value.
Okay.
So my next question would be, is this a convolution as far as you know about discrete convolution operation? Is what we just saw can be considered as a convolution? What do you say?
No, because usually you flip the kernel.
You fit the kernel, what do you mean?
Flip.
Oh, you flip, yeah, so you're exactly right. Yeah. You flip the kernel. This is exactly right. But let me just say it more accurately. This is not exactly, this is right, but not exactly right. This is a convolution, just not with this filter, but with the flip of it. So in convolution, you take the flipped function. Also, we can think about continuous convolutions. You flip the function and then you do this process that you've just seen. So this is a convolution with a flipped filter. And if you want to be more accurate, so we're doing what's called cross correlation with this filter and not a convolution. So yeah, it's really weird and sad, but a convolutional layer should have been named a cross correlation layer. Okay, but this is how life goes. Okay, so let's get ourselves familiarized with the concept of stride. So stride basically means that the filter is now going to jump. It's not going to just take one step each time, but it's going to take more of this. So for example, stride 2 is going to look like this. You see the filter is located here, but now it's this black weight is not going to be located at x1. It's going to jump over to x2. So this is called a stride of 2. And you can see that a stride is a reasonable way to do downscaling to your data. So if you have some size, some number of neurons in some layer and you want to have less of them, so a very reasonable way would be to use stride. And we can look again at the matrix that we had before. This is not the correct matrix for what we have now. This is what we had before, and we can think of how we can express the matrix that matches this stride of 2. And one very easy way to look at it is to say that this is the same as doing this stride 1 convolution as we've seen before. Only then after it, I just drop every even output that I have. So I can take a look at the lines of the matrix, of the rows, sorry, of the matrix, and say, okay, so I'm going to drop this one, that one, and that one, and this is how the matrix is finally going to look like. So this is how a stride 2 convolution would act. Okay, is this clear? Are we good? Okay, great. So this is called stride, and now let's talk about padding. Okay, so let's say that we want to have an output with the same size as the input that we have. So what we would usually want, the reasonable thing to say is that I'm just not going to use all the weights. So we had this black weight, and it's now I'm just not going to use it, and I'm just going to use these two, and then this would be this would define the output that we weren't able to define before. So the thing is that I have my filter stuck here at the end, and I can't get him to get higher. So I'm going to do something that is very common and used a lot also in the world of signal processing or whatever. And I'm going to do, for example, zero padding. Okay, and I'm going to add these two neurons, 1 0 here and 1 0 at the end. And now when I do this convolution, I just do a regular convolution, and I'm getting exactly what I wanted because the black weight is now multiplied by 0. I don't have to pad by zeros. There are many other ways you can pad. You can do a thing called mirror padding, reflection padding. You can just repeat the last value. There are many methods, and it really depends on what you want to achieve by that. But the basic thing is zero padding. Okay, now I'm able to get output at the size that I wanted, and when you want to have the exact output size as the input size, or if you have stride, you want it to be, for example, you have stride 2 and you want to have exactly half of the size. So this is referred to as padding, and this padding style is called same. Same padding means you want to have the same size. It's not in PyTorch, you don't do that. You don't write same anywhere, but it's just like this. I think it still exists in TensorFlow, but same padding is just a figure of speech to say that we want to have the same size. And I should also mention that sometimes you have to pad. It's not a matter of preference, because if you use stride, for example, this is stride 2, and you don't use padding, then it's going to be undefined how to act, because you look at this filter, so it jumps over here, and now we have this last x sub 5 input, and we're not able to use it. So it's not defined how to act in a situation like this. So sometimes this is called a valid padding to make the input valid for this convolution, and we can add this 0 here, and we'll have another output neuron there, and so this is the type of cases where you have to pad. So people sometimes say we have a valid padding and same padding, okay? And so far we've seen the basic tools for convolutions, and we looked at one dimension. But remember that our goal here is visual recognition. So we want to deal with this spatial 2-dimension structure to be able to process it. So our next step would be what we call conv2D, okay, the 2-dimensional convolutional layer, and the expansion to 2 dimensions is not super trivial. It's not hard, but it's not super trivial. There are some more elements that are now defined. So we're going to be working with tensors, and the regular order of the tensors that we work with in visual recognition are going to be tensors of order 4. And why 4? So the first dimension n is the batch size. So we're always working with batches. Even if we don't want to use batches, then we'll say that we have a batch of size 1, then n will just be 1, okay? And h and w are height and width. They are the spatial dimensions, okay? So as we have in images, think of an input image, but it doesn't have to be the image. It can be any later representation inside the network. And what we call C here is the channels, and the channels is another element that we have, which is different from the spatial dimensions in the sense that we're not going to do convolution over this dimension. The convolution is going to happen just on the H and the W. I'm going to show it in a second, okay? And the channels, and just for this intuition in the meanwhile, the channels are going to be sort of these fully connected, locally fully connected elements that you're going to look at. So as for the channels, when I look at this, you know, one square here with the same, with one value for H and W and all its channels, then for these channels, it's going to act sort of like the fully connected that we had before. And we're going to intuitively understand why we do this very soon. And how would this convolution work? We're going to have this filter, and this filter for now, just for now, is going to be a tensor of order 3. And it's going to have channels and small h and small w for height and width. And the channels that we have for this filter have to be the same. We have to have the same amount of channels as we have for our input. Otherwise, it's not valid. We can't do it any other way. They have to be the same number. C here and C is here. And small h and small w are like the 3 that we had for the one-dimensional case. So we have 2 special dimensions for our filter. Okay, so we have C, H, and W for the filter, and we have N, C, H, and W for our input. And when we apply the convolution, this is sort of how it's going to look. So this filter is going to travel along the input. Every time it's going to jump according to the stride. We have in this example 27 weights, 3 by 3 by 3. All the 27 weights multiply the 27 inputs that they now see, and they sum it up, and then we have one value that we put in our output. But notice how we keep the geometric, the special 2 dimensions. So we're not flattening anything. Okay, we just travel along now along these 2 special dimensions, and we can go on and on. And the filter just goes according to the stride, and then we get our output. So the output tensor now is going to be n, because n doesn't change at all. We have, this is the n is the batch size that we have. Okay, and we have h and w that are somewhat different, and this is according to what we discussed before. So it's a function of the padding or the stride and all these things. So it doesn't necessarily have to be the same h and w. These are modified h and w. And currently we have just a single channel, right? Because we have just only this green set of outputs here. Okay.
Assaf?
So far, any questions? Yeah.
Can you explain again what is the n batch size? About what?
So so do you remember we work in mini batches? Okay. For example, in optimizing a neural network. So it means that I have this input here. You see here these 3 dimensions. You see C, H, and W. But I have not just one of these. I have many of these, n. Let's say 32 or 64 of these, and they're entering the network. Usually, when you want to do this computation efficient, they enter the network in parallel.
In pictures, it's meaning few pictures.
It's many pictures together. It's many images together. Yeah.
Okay.
And let me just state that until now, all the actions that we've seen until today, and also including today, only until next week, all the actions and operations inside a neural network that we've seen don't really care about the batch. So you can do them one by one, and then take the average of the loss and the average of the gradients to optimize and whatever. Okay, the first time that you're going to witness something that does some operation along the batch dimension is going to be next week. Okay, but so far we haven't seen it. But computationally, it's going to be parallel. This batch of images is inputted together, and this is what we get. Now, let me ask you this. Sorry, let me ask you this. If I do this operation the way I just suggested, so the output will always just have a single channel. So the next convolutions from now on are all going to be with C equals 1. And of course, I don't want this. I want to be able to represent my data with more features. So any suggestion what would be a reasonable way to have more channels to the output?
Just every layer RBG is for itself.
So I wouldn't recommend. I mean, this is a thing that you can do, and from some reasons people sometimes do, but usually it's not what you want to do, because you don't want to have the green channel processed differently from the red channel. You want to look at them together and to have your conclusions. Any other thoughts, any ideas?
You can use several channels.
Okay, so you can use several filters. This is correct. So we have this green filter here. This is just for marking it. It doesn't say anything about true colors. We have this green filter here and this produced this green output. But now I can have another filter, let's say the red filter. And from the red filter, now I can have the red output. Okay. And I can have many such filters. Okay. And the way to express it is say that also the filter is going to be an order 4 tensor. Okay, so now we can summarize the operation of a 2-dimensional convolution. Okay, so the input is what I call N, C in the number of input channels, H and W. We know the meaning of, for all of those, we are aware of the meaning, right? H, C in, W. As for the filters, we're going to have, you can look at it as an order 4 tensor or as a set of filters, of 3D filters, whatever you feel like and the way it's comfortable for you to think about it. But you finally summarize it as an order 4 tensor, which with the dimensions C out, which is the number of filters that we have. So we have in this particular example, it looks like C out equals 2. Usually you'll have much more than that, like 64, 256, whatever, maybe a large number. So C out is the number of filters, because this determines the number of output channels that you're going to have. So you see, you have C out here and C out there. And the dimensions we've seen before, C in, small h, small w. Okay, these are the size of the filters. And naturally, the output you're going to have is going to be n, C out as determined by the number of filters that you have, and the modified h and w. Only just keep in mind that the filter must have the same C in as its input, otherwise it's not applicable. And the output must have, and it's out of your control, this is just what you're going to get, the number of channels that you're going to get C out for the output is going to be the number of filters, the C out as defined here. Okay? So are all these dimensions and tensors, everything is clear? Are we good? Are we okay?
Just a question. What's the difference between one filter and the other? I mean, we've seen only summation by now. And what else?
So the red filter has different weights from what we have in the green filter. It's just convolving with another filter, which is different. Okay? Okay, thanks. Make sense? Okay. So this is how we roll. This is how conv2d works. Okay, we always have these the batch channels H and W, and I think that we will have our break now. So let us have a 10 minutes break. Okay, you know what? Let's make it 15. Let's have a 15 minutes break. Okay, and we'll 10:15 exactly. Please be here at 10:14. Okay, so we just can continue. Okay.
Assaf?
1 sec. Okay, so everybody's here. If you can turn on your cameras, it would be great. Thanks. And okay, so before we took the break, please mute yourselves. Okay, 1 second, sorry. Okay, so before the break, we got ourselves familiarized with 2D convolutional layers and all these tensors and sizes. But now I want to go back for a second to look at 1D convolutions. Okay, so and this is to introduce what we call receptive field. And for this sake, I want to ask you, if I look at this neuron right here, x super 2 sub 3, can you tell me, and let's say I'm using a filter size of 3 again. Can you tell me how many neurons from this layer here, from layer number 1 here, how many neurons from this layer affect this neuron in layer number 2 here?
3.
3. That's right, and this was an easy question. But a more interesting question would be, how many neurons from the input affect this neuron that we have here, x super 2 sub 3? What do you say?
9.
So I heard 5, I heard 9. The correct answer is 5. Okay, and it's very easy. It's very easy to calculate, because what you have to do is take all the neurons that affect this neuron here and see who the neurons that affect them. And this is easy to do this way. And you can see the correct answer is 5. And again, you have this really petty calculation that you can do, take into account the sizes of the different filters and what you need to add, and then you can think what happens when there are strides. And I'll leave all these things to you to think about. These are easy calculations to do. We're mainly interested in understanding the way that the receptive field behaves and what it actually means. Let's try just another one. What if I look at this neuron right here? What do you say? How many input neurons affect it? Any idea?
7.
Yeah, so the correct answer is 7. You can do this way. And this is what we call the receptive field, okay? The receptive field is an extremely important term for us, because it teaches us that each feature that we have somewhere in our network is only just affected from a certain patch from the input image and not the entire input image. And you can see already several characteristics of the receptive field. For example, we know that the deeper we go, the receptive field grows, right? We've just seen this. Okay, let's take this again to 2D. Okay, so say I have this input image right here. Now I'm going to look at a feature map that is adjacent to it, like the next layer, and I can I can calculate the receptive field as a function of the filter size and get a certain size. And you see that specifically this pixel here, so the set of neurons that are in the channels, but that are located spatially at this location, we sometimes refer to them as pixels, even though they're not pixels, they're not picture elements, but it's easy for us to name this way to all the channels in a specific spatial location. So this pixel here is affected from, say, a bunch of input values that we have here. But if we look at the next layer, then we can do roughly the same map we had before, and we can say that in this layer we have this pixel here, and it is affected from all the pixels here, and each one of them is affected from pixels here, and this is why we have a larger receptive field. Okay, so two things are happening here, and these are very related to things that we wanted to achieve when we discussed it at the beginning of class today. So one thing is that the deeper we go, the larger we see the field of view. What we now call the receptive field grows the deeper we go into the network. This is a thing that we wanted to achieve. But also another thing happens, and this is that the complexity of the function that the feature represents, the feature is a function of this receptive field that it sees. This function gradually, the deeper we go inside the network, this function gradually becomes more complicated. So as we wanted before, the first layer, think about it, it only does this linear thing, right? So it is perfectly good for recognizing, say, corners and lines, or loving the red color or the purple color or whatever. But it certainly is not able to recognize faces or eyes or hands or legs or anything like this, because this is only multiplying a set of weights by a set of values. But if we use a nonlinearity and then another convolution and another convolution and nonlinearity and convolution and nonlinearity and so on. So just as in the fully connected case, in the MLP, the multi-layer perceptron, so just like in this case, we're getting a more complex representation that can be highly semantical, like identifying faces, for example. And so these are two things that happen gradually. The deeper you go, you see more space, you see a larger receptive field, and you analyze it more complexly, if this is something you can say. Okay, and so we can summarize so far all these characteristics and see what we have achieved. So let's think about it together. So what we wanted is to maintain 2D structure logic. And as you've seen, we're not doing this thing that you're, for example, now doing in your homework or done before, this reshaping. We're not taking the image and reshaping it to this one long vector, right? We're not doing this anymore. So we maintain this 2D structure along most of the network, okay? The other thing is shift invariance. And it's very easy to see that if you shift your image, then everything you have is shifted, because just the filter acts the same. It's only doing this in another place, right? Are you with me? Are we okay by now? All right. We only consider local correlations, and this is obvious because we have this filter, right? So you can only see what the filter sees. You can only see what's in this small receptive field to one layer back at each time. These are the correlations that you can do. And it's true that if you go deep enough, then you get these correlations from areas that are far from each other inside the input image. But this happens gradually, and the correlation is between more complex concepts that each of them sort of summarizes the receptive field that it sees. We also have this hierarchically growing field of view. We've just seen it happens and this hierarchically progressing complexity that we just discussed. And this is important because this means that roughly what we started today's lecture with, looking at this desk and saying, you see the key and then the keyboard and so on. So this is exactly how these set of convolutions work. You first identify simple, small elements. Then at the next layer, you use what you identified at the previous layer, and now you're able to aggregate them and to understand more bigger concepts that are more complex. And gradually you go on, and you start from vertical lines, vertical and horizontal lines, and you finally get to eyes, nose, faces, humans, motion, whatever. Okay. And last thing is reasonable amount of parameters. And we did this math before, and we got that when we found out that fully connected layers require a huge amount of parameters, probably unreasonable. But convolutional layers have much less parameters. We only have what we have in the filters. So the number of parameters we have is just the size of the filter tensor. It's for 2D convolutions, it's these 4-dimensional tensors, C out, C in, H, W. H and W tend to be small, they're not big. So at big networks, it can be big numbers, but it's nowhere near this 10 to the 13 that we've calculated before. And another nice thing is that it's invariant to the size of the input. I mean, to the spatial size of the input. Okay, you can have 100 by 100 image or a 5,000 by 5,000 image, but what determines the number of parameters is the size of the filter, not the size of the input. So are we good by now? Okay. Okay, great. So let's introduce another concept, and this is called transposed convolution. And you may bump into the terminology that says deconvolution. Some people call it this way. It's a wrong way to call it. Deconvolution in signal processing is a different thing, but still some people call it this way. But the correct term is transposed convolution. And again, we use this color coding ABC over here. And this is how transposed convolution work. So we look at the inputs and we say, okay, let's take this X1 input, and differently from convolution, instead of this aggregating, what I'm going to say now is I'm going to take the same value, the value that I have in X1, and I'm going to multiply it by A and send the result here. Then I'm going to multiply it by B, send the result there, and by C and send the result there. Okay, so it's something, it looks a bit different from convolution. And then for the next step, I'm going to take one step here, and I'm going to do the same thing. And neurons that are now connected with more than one weight, I'm just going to do aggregation. So I'm going to take the sum of these values that I sent to them. Okay, and can go on. And I can do, we can say something about it later, the way we pad in transposed convolution, but I can do this padding and also have the entire size. And can you guys help me now? And what the matrix is going to look like? And because it's still a special case of fully connected. So what do you say? What would you expect the matrix to look like? Any thoughts? I'm not. You don't have to say like something accurate, like with respect to the convolution matrix that we've seen before, or anything like this.
It's the same, just transposed.
It's the same, just transposed. So we'll get to this transposed, but right now we can say something actually simpler, right? And so here's how it's going to look. And before we had ABC, and now we have this CBA. The comment about transpose is correct, but we can say something just for this slide. We can say something simpler. So it turns out that if we take the filter and flip it, then we'll get the same thing. So this is a convolution. What we got here is actually a convolution with the flipped filter. Okay, this is what we're getting. So far, transposed convolution is not that impressive. What turns out is just that it just does convolution. But now we can define the concept of stride for transposed convolution. And the thing is that transposed convolution, so far we know about convolution with stride 1, and we know about convolution with bigger stride, like 2, 3, 4, whatever. And we know that stride makes our convolution do downscaling. So we get a smaller output than the input that we had. But we never talked about a way to upscale your input. If you have some input and you want the output to be bigger. And this is where a transposed convolution with stride enters the picture. So let's say I have this input of 3, and I want to have a larger input, say for this example 7. So the stride for transposed convolution is applied not on the input, but on the output. So the way it works is this way. We have these three weights here, but if you look at the output, you see that the black weight that we have here is not connected to this x1 here. You have a stride of 2. It's like if you look from the right to the left, then you had this jump of 2 and not a jump of 1. Okay. Now, if we want to characterize it in a matrix again, so this is not the correct one now. This is what we had before. Okay. If we want, so you remember that when we did stride for regular convolution, so we just deleted some of the rows because we said, okay, we do just a normal convolution, but some of the outputs we're not interested in. We're throwing them away, right? So now what happens is that some of the inputs we're not interested. I'm not sure what I said before. What I should have said before is some of the outputs we're not interested in them, and now some of the inputs we're not interested in. Okay, so we're just going to delete some columns. Okay, and the matrix that now depicts the operation of transposed convolution. So it looks like this, and this is not a special case of any convolution or strided convolution that we had before. We can see it's very nice and interesting, but it's different. However, let me remind you how a stride 2 regular convolution that we used for downscaling looked like. And this is how it was. You see this ABC, ABC, ABC. We have here ABC, ABC, ABC. And now I think it should be clear to everyone why this operation is called transposed convolution. Because if you use the same stride and you're careful with padding stuff, okay? I'm doing here, I'm not sharing with you some like tiny annoying things about padding that would have changed these little things here. But if you're careful with padding, okay? So transposed convolution is rightfully deserves its name because it takes the linear operation and uses its transpose. Okay, so far are we okay? Everybody's with me? And this is the most basic way to upscale. Okay, to get a bigger output than what you had. It has many problems. It has many artifacts, and I can send you later. There is a great publication, distilled publication about it, about a thing called, you can look for it, the checkerboard effect of transposed convolution. And this is some artifact that we sometimes get when we use transposed convolution. So you can check it out. It has these really cool animations that explain it very well. Okay, here's something that we need to notice, and this is that you can express a transposed convolution by a convolution if you do some modifications to the input and filter. So what you can do is do this thing called dilation. Dilation means that we add zeros between our input terms. Okay, so instead of having this, we now have 0 this, 0 that, 0 that, and this is called dilation. And the other thing I do, if this is my filter, now you need to stare at the filter to see what's going to happen. I'm going to switch now. I'm going to flip it, so the black arrow is going to switch places with the green arrow. So you see, so now the green arrow is up there. And if I do this flip and dilation, and then just a regular convolution, then now I'm getting exactly what I wanted. You see that Okay, the matrix also flips. And again, I can now delete columns because these columns are 0. Okay, I added these zeros here, and I get exactly the same as before. So you can get transposed convolution by dilation and flip. The size of the dilation that you do should match the size of the stride that you want to do the transposed convolution with. So this is called dilation 2, even though I had only 1 0, because dilation 1 means no dilation. Okay, so this is called dilation of 2, and it matches a stride 2 transposed convolution. Okay, are we good by now? Is everything cool?
Assaf, for the neuron x0l+1, here it receives weights from which neurons on the previous layer?
So, okay, so this depends on your padding. So in this particular example, I probably shouldn't have put it here at all. It's because you're not going to get any output here. So you see this actually matches this starting from x1. But if you pad, you can add, padding is like orthogonal to dilation. You can do dilation and then you can do padding. Okay, and then you'll get your output here. So since we are now defining this as a convolution, not as we want to achieve transposed convolution, but we now express it as a convolution, then you do the padding here. Let me just say something that we haven't mentioned, is that for transposed convolution, we sometimes pad the output, right? We can look at it for a second. Okay, the way we've seen it, for example, here. So think about it. If look here, if we sort of want x0 to join our game too, but to do this, we need to sort of pad the output because we want to send some values on these arrows that will get nowhere. So you can see that there is a black arrow here going to some output we're going to just throw away. Okay, so this is padding the output. All right. So one thing we're going to, yeah.
You said dilation 1 and 2. Can you explain what do you mean? That one is
so dilation 1 basically means no dilation. Dilation means you sort of expand. Okay, you expand every neuron. So dilation 2 says that now I expand, and this neuron that was just in the size of 1 neuron, I expand it to be 2 neurons. Okay, so dilation 2 is expanding the size of your vector or tensor or whatever by adding these usually zeros, but it can be, you can put here other values.
Dilation I means that every neuron is the size of I.
Yeah.
Oh.
Okay. So one thing we're going to only briefly discuss, and you're going to probably work hard on in your homework, is how do you backprop a convolution? And let's talk first just about 1D convolution. So I want to ask you, if anyone has any idea, of a way to do backpropagation for 1D convolution layer? Any idea here?
It should be similar to just a linear layer. If
right.
Because we can, it's just a case of linear.
Yeah, this is a good direction, right? So Raphael says this has to, we can just think about it as a special case of a linear layer, of a fully connected layer. And now we can think together. So how do you backprop through a linear layer? What do you do? Anyone remembers? Anyone? So if I have matrix multiplication and then I want to do the backward process of it. So how does this work? Any idea? So last time we met, we had this linear layer followed by non-linearity, a ReLU or whatever, right? So now we just don't have this ReLU. So if you have the gradient of the output, how do you propagate it to get the gradient of the input? Remember? So I'll remind you that the way we do it is we just take the transpose of that matrix, right? Because We saw it last time. We think about a linear operation, and then you take the derivative of the output, and then you use chain rule to get the derivative with respect to the input. Okay, so the backward process is taking the transpose of that matrix, and we actually know by now how to take the transpose of the convolution that matches of the linear operation that matches a convolution layer, right? How do you take the transpose of it? Do we have a name for this operation? For the transpose of convolution?
Transposed convolution.
Yeah, so it's called transposed convolution, right? So when the forward process is a convolution layer with some filter, then we can just do the transpose convolution of it, okay? This is simply by thinking of it as a linear layer. Now, the same logic applies to 2D convolutions, but you have to be a little bit more careful because you have these channels now. And as I mentioned before, for the channels, C in and C out, it's like, you can think about it like a fully connected network that travels around your input and output. Okay, so first you also need to transpose C in and C out. You need to switch them. And then you need to do a transposed conv to D. And for the transposed conv to D, you can use our trick of dilation. You can take the input, dilate it, and then flip the filter and then apply a convolution. You need to be careful with padding so that you get the same size. And in your next homework on CNNs, you're going to implement this thing exactly. But you're going to, we'll guide you there. You're going to be thinking about things called folding and unfolding. So there is a basic trick. So you don't want to have this huge matrix that is mostly zeros. So what you can do is you can do this taking a list of patches from your input image, okay, and use more memory to represent your data with much more redundancy, but then with a simple multiplication by the filter, then you're able to be done with it, and you don't have to actually define this huge matrix that is mostly zeros. Okay, so this is just a note about the backprop. All right. So more or less we've been through most of the basic operations about convolutions that we need to know about. And there's one more we're going to discuss in a few minutes. But more or less we're done with all the basic operations. Let's try to have some intuition, to understand some facts about the behaviors of these convolution layers. So,
Assaf, some small question. The usage of transposed convolution is only when you do backpropagation, or you have some usage for it, like in a normal way?
Yeah, a great question. So no. So you sometimes also use transposed convolution as a forward operation, and this would be when you want to do upscaling in a network. So when do you want to do upscaling? So there are some examples. So the first one that you're probably going to bump into, it's in 2 weeks from now with Shai. You're going to discuss object detection, and these are networks for object detection or segmentation or stuff like this. These are networks that tend to have what we call an hourglass architecture. So it first does this downscaling, and then it goes back. It does upscaling. And there are some ways to do upscaling, but the most basic one is this transposed convolution. And there are many other use cases where you want to do upscaling inside the network. Okay, so we know the basic operations by now, and let me just define that we usually refer to these outputs of layers inside our 2D convolutional network. We refer to them as feature maps. Okay, so the result of each such layer, this tensor, this order 4 tensor that we have, we refer to it as a feature map. And And I think it's really important to look at this in these two ways to intuitively understand what we're getting. And I just want to remind you that one of the key aspects of deep learning in general that we discussed in our first lecture and actually in the second lecture too, is this hierarchical representation. So every layer actually is just a representation of the input, but with a different type of representation that gradually becomes more useful to the final task of the network, okay? Because at the end of the network, we do a very simple thing, but the great thing is creating very great, useful features for it to be able to do its job well. So at each layer, we have this, the result is this feature map describing the input, and there are two ways to look at it, two intuitions. So here's one of them. What if we take one of the channels of this feature map tensor, okay? Now we look at it and we analyze what we see in it. So each such channel is a relatively shift equivariant function. So if you move things, the result here will also move, almost. There are some things you can say about this. I'm not going to get into it now, okay? And the way it works, and some of you who are experienced with convolutions, with mathematical convolutions, know that the way it acts is that convolutions work a lot like template matching. So the result of a convolution will have the highest peak in places in the input that are very similar to the filter. And when you have a set of these convolutions with nonlinearities, it's going to be a bit more complicated than this, but the general behavior is going to be that some channels in some feature map, they like certain things. And the reason it's called feature maps is that, think about it, this is just a single channel. At every spot we can have this value, and high value means that it likes what it sees. These feature maps tend to be very sparse. It's going to be mostly black, but each channel learns to have its own job. So just for the illustration, this channel in this feature map, for example, this is a channel that likes human faces. So it has high activation. We get high value when the position matches the position of a face in the image. Assuming training went well, learning is good. So it is really, and in a few lectures from now, you will be able to analyze this and to see really ways to actually check it by yourselves. So each such channels maps where it sees certain things that it likes, so that the next feature map can say, oh, I see. And this brings us back to this logic that we had at the beginning of the lecture about this hierarchical representation. So we can say, okay, so in layers that we had before, there was the channel that likes noses, and there was the channel that likes eyes. And then the next channel said, oh, I see. So we had nose here and eye there and an ear there. So I see. So this is a face. Okay. So a linear operations over nose, eyes, and ears equals a very complex nonlinear operation over the input image, which is recognize a face. So this is built hierarchically. So this is a first intuition, and this is really how it acts. If you look at these tensors of these feature maps, you see it tends to be very, very sparse. You only see for some channels, for some locations, you'll see that it recognizes things that like it has high values. If you use ReLUs, then the minimum you get there is 0. So you can sort of distinguish between 0 or values very close to 0 to high non-zero values, and this is where it sees the things that it is looking for. But here is another intuition. Now, why don't we're not going to take a full channel. Now we're going to take all the channels, but just in one single spatial location. We're going to take this needle, okay? And this needle is a pixel, and it has its own receptive field. So it sees some patch from the input image, and it has some sort of coding that describes what it sees. So the deeper the layer is, this coding is more semantic. It describes in some way that the next layers can read. Us humans usually can't figure out what it means, but it has this coding that says what the network sees in this position and in the analysis level of this particular layer. Okay, and another way to think of what happens in the next layer is says, okay, so here we had something that is described this way, that in some language may say that there is a human face here with some background, with some blue shirt, whatever. And in another place we have this thing saying that I have here a shoulder with a jacket and this road sign over here, and then aggregating all these things together, say, okay, so now I can understand what I see. So these are two different angles to analyze how feature maps represents what we have in the image and how we use it for the next layers. Any questions by now? Are we good? Are we okay?
Assaf?
Yeah.
We said before that each layer sees more from the picture, but
right.
Here you said that this needle sees the same location. But as we go with the layers deeper.
Yeah, when you go deeper, then you have needles that see larger patches from the image. Okay, this is some layer. This is some specific layer, right? The next layer will have a bigger receptive field and so on. Okay.
Oh, this all is the same layer?
Yeah, this is a feature map. You see, this is channels, height and width of the same layer.
Okay.
Okay.
Thank you.
Regarding to this, I also want to mention that when you have very big networks, and we have it's very common to have networks of, so it's very common to have, like, for example, 155 layers. Okay, it's the thing you do. Then probably the receptive field of pixels that are in layers that are very close to the end of the network, for their very deep layers, they will probably have receptive fields that are actually bigger than the entire image, which is okay, which is great. Okay, we'll know that it is a great thing. It does make sense. I want to introduce quickly a very simple procedure, a very simple operation. This is called max pooling, and it's also sort of inspired from the human brain. And this is a basic operation that does a simple thing. So you have this window, very similar to the way convolution operates. You have this window, this filter going over your input, and every time it does this non-linear action of choosing the highest value that it sees. So you see, so when we have 7, 3, 8, and 7, so the winner here is 8. And so on 5, 2, 1, and 6, we have here 6. And we should, and I should mention that usually, like the basic thing that we usually do is that the stride of this window equals the size of the window. Okay, so you don't have overlaps. And this is another way, as opposed to strided convolution, this is another way that we have for downscaling. And this is a very efficient way. It has no learnable parameters at all. This is non-linear, and this was proved to be very efficient, and it is used a lot. It makes a lot of intuitive sense, but I think if I'll try to explain it, I'll get too philosophical. So you can think about it yourselves. So the direction to think about is what I care about. If I have a lot of background, and in this background I have a hat, so, or anything else, I have an eye, I have someone, I have something. So what I care about is not the background. I want to represent this large window. I want to represent it by what's important. So looking at what we had before, we had each channel likes other things. So if all the channels don't recognize anything, everything is black, but at some channel we have high value at some position. This is what I want to keep. I don't want to average it, and I don't want to do anything else. And this was shown to be very efficient. And technically, you should notice also that each channel is operated separately, right? This is only for one channel. and then you do it for the other channel the same way. So it doesn't change the number of channels that you have. It changes only the amount of spatial dimensions that you have, and usually it's the most it's the best way to do downscaling, and it's very common to use a stride of 2 and window size of 2, and then you have exactly half of the pixels that you had before. Okay, are we good with the max pooling? Okay, and I should mention that there are other things. There's average pooling, which I'm sure you can guess how it does, and other ways, but this is like the most common and most useful. And we're almost done here. I just want to put all the things together and to show you how a very small typical CNN would look like. Okay, so the way you operate is conv value, conv value, conv value. Okay, the same you use non-linearity, the same reason we used it with the fully connected layers. Okay, a convolution is still a linear layer, and if we don't have non-linearities, we could have expressed the entire network just linearly. Okay, so usually you do conv value, and then from time to time in your network, you use max pooling to downscale. You can also use a strided convolution, okay, or use max pooling. And at the end of the network, how do you finally make it a classification, for example, or how do you go to the task, the recognition task you want to go to? So what you do at the end, when you have, usually you'll have a very small tensor spatially, like maybe 14 by 14 or 7 by 7, because you had many poolings or strides. Then you reshape it, and then you apply this regular linear layer. Okay, it can be 2, 3, 4 linear layers, and from here it's just as you know for the multi-layer perceptron that you're now doing in your homework. So it's going to be just linear layers, and then for example for classification you can use softmax plus cross entropy loss. Okay, for regression you can do other stuff, but this is how we usually do in recognition. So we do a lot of convolutions until we get a very small representation, spatially small, and then we reshape it, and we have these fully connected layers. Let me just say another thing is that typically what you're going to see is that the deeper you go in the network, so the spatial dimensions are going to get smaller, but the number of channels is going to grow. I tried to draw it here. You see here you have only 3, and now you have spatially smaller but more channels, and here's spatially smaller but more channels. And the intuition behind this is this needle intuition we've seen before. So the deeper you go, you're saying, okay, I don't have to remember exactly every pixel where it was. I just want to remember, for example, if I want to do classification and I want to know that what I'm seeing now is a dog. So it's important, it's only important for me to remember that at the top of the image, I saw the head of a dog, and at the bottom, I saw legs, dog legs. It's not important to me what was the exact pixel. So this is why the resolution can gradually get smaller, but I have more channels because the concepts are getting more complicated, because at the beginning of the network, I'm saying, okay, I see brown here. I see a brown pixel here. This is very easy. I can express it just with the 3 numbers, okay? But if I want to say I'm seeing a dog here, then I need to have a much larger such needle. Okay, I'm referring to the needle we had here. Okay, I need more values to be able to code a more complicated concept. So the deeper we go inside the network, the resolution decreases, but the channels increase to be able to describe a more semantic, more complicated concepts. And this is the really just the basic network, and you're going to discuss many architectures and many other cool tricks. I want to mention just a few things that exist. So there's a thing called, someone actually suggested it earlier today. There's a thing called depthwise convolution. At some cases, you want to do convolutions separately for each channel. These are very special cases, but you should know this term exists and you can do this. Okay. And there is a thing called group convolution, and this was first introduced in AlexNet. And this was mainly for having less parameters, having more efficient computation. So you say, I don't want to connect all the output channels to all the input channels. So I'm going to have these groups. Okay, these outputs are only connected to these inputs, etc. And this was used. This today is used for efficient computation, and for AlexNet it was used because they had to, because they used 2 GPUs to perform the network, and technically they had to sort of split their network in 2, and they had to do this. But this was shown to be very efficient, and for efficient networks like those that we want to apply when we're using our cell phones and stuff like this, so people tend to use this thing. And at some point, you and Vladlen Koltun, they introduced dilated convolutions, and this is just a convolution filter with holes. And this is sort of a way that you're now able to have higher receptive field, but preserve the resolution that you have. Okay, you can think about it as a solution to this. You can read it's relatively not that old paper from 2016 when they introduced this. So all these things exist, and many others. There are infinitely many tricks and variants of convolutions, and there are deformable convolutions and whatever you want, really creative and interesting stuff. But these are like basic things that are now used. So if you use a convolution layer of PyTorch, so one of the arguments that you can provide is the number of groups or the number of dilations. So this really merge into the basic concept of convolution layers. So this is why I'm reminding them, okay, the number of groups and the dilation. That's it. We're done for today. And you're not going to have a tutorial this week due to Memorial Day and to Independence Day. But next week, Shai Bagon is going to give a lecture about practical training. And the point of this of the next lecture, as you can see the meme over here, is that what I was teaching until now was very let's say too optimistic. So by theory, we're able to do all this stuff that we discussed. But if you want to get good results, then this is not enough. So if your neural net may sound like very elegant and doing cool things, but you need to use many other tricks and elements and stuff that, like smart initialization and data augmentation and user regularization and a thing called dropout layer and batch normalization layer, and to think how you do hyperparameters tuning. And so all of this you're going to do next week with Shai. And after this, you will really be able to very efficiently train recognition models and get good results. Following Shai's lecture, you'll have a tutorial by Dlo about CNN architectures, and you'll see like along the years chronologically, you're going to see the elements that were added and the tricks that were added and used to achieve good results in visual recognition models. All right, so by this we are done. I want to thank all of you. Thank you for listening. Thank you for being with me, and we'll see you next week. Thanks.
Thanks.
So if you have questions, let me just one second stop the recording, and I'm coming back to you.